One thing that this emphasizes for us is this object speeding up or slowing down?
Slowing down.
Right, even though its acceleration is positive. So notice that positive acceleration doesn't tell you whether you're speeding up or slowing down, because obviously whether this is positive is just arbitrary. It just depends on what we chose as our positive direction. But oftentimes people get lazy and they think that positive acceleration is acceleration and negative acceleration is deceleration. Well, it doesn't work that way because it all depends on what you chose as the positive direction. What we said earlier is the way to think about it. What matters is whether the sign of the acceleration is the same or different from the sign of the velocity. Here they have different signs. That's how we know we're slowing down. So we can't just look at this sign in isolation. Then you pick the right equation. You pick the equation that's missing theta. Omega final we don't know. Omega initial is negative 1930 radians per second. The acceleration is positive 81. And I'm going to keep putting in the signs because I really want to make sure I'm not forgetting the signs. And the time is 10 seconds. In this case, the signs kind of work out nicely, so you want to go ahead and put those in. These signs would cancel. So, what answer did you get?
I got negative 1,120.
And what units?
Radians per second.
Are those the units that we would have expected?
Yeah.
Yeah, so the units worked out nicely here. We should check whether this makes sense. According to this number, after 10 seconds, is the wheel moving clockwise or counterclockwise?
Clockwise.
Is that what we would have expected?
Yeah.
Yeah, because it started clockwise.
Right.
Presumably, it's going to keep moving clockwise until it stops altogether. Presumably, it's never going to start working. It's never going to start going counterclockwise because they're just turning the engine off. So it's always good to check whether your answer makes common sense. For example, if you hadn't put in this negative sign, the first answer you got was positive.
Yeah.
Well, that should have been enough by itself to tell you that you made a mistake, because that was telling you that the rotor was shifting from clockwise to counterclockwise, which doesn't make sense for this problem. So it's always good to think about the common sense of the problem. Well, now, what then is the answer to part A?
It's negative 1,120 radians per second.
Good. Now, if your instructor is a real stickler for detail, they might take off a point there because they were asking for the angular speed, not the angular velocity. And speed is the magnitude. So the angular speed is just 1120 radians per second. I've kind of invented a symbol that I find useful. When I'm focusing on a magnitude, I put a dot on top of something. So actually, technically, they were not asking us for the angular velocity. That was just a sub-question. What they were actually asking us for was the angular speed. The instructor would have to be pretty picky to actually take off a point for that. But anyway, technically, we would give this as a positive number. Well, we learned a bunch of stuff from this right here. You can see that the picture doesn't have to be all that complicated. But one thing I should have put in the handout is draw your positive direction and actually draw the direction of the acceleration and the angular acceleration and velocity, because otherwise you can't decide whether they're positive or negative, which is one of the most important parts of the whole problem. And again, while using the approach that we're using here, we would use a curved line to show the direction of the rotational variables. And don't confuse these with the linear variables. You don't want to start drawing the centripetal acceleration, because that's not a concept we're using to solve this problem. Make any sense?
Yeah.
All right. Well, let's take a look at the next part of this problem. Let's try part B. And again, we want to use the same systematic techniques we used for part A. pretty much perfect. Very good. That's some good progress. One thing before I forget, now on the test, all the different types of problems are going to be mixed up. So how would you know that this is a rotational kinematics problem if it was on the test? Are there any clues here that this is rotational kinematics? Well, one thing you should notice is that they're dealing with the kinematics variables. In fact, they're not dealing with anything besides kinematics variables. That would be a big clue right there. That's one good reason to memorize the kinematics variables. Another point is we know that we do have a constant acceleration because they just gave us a single number for acceleration. They didn't say it was constant, but that was implied. Otherwise, how could they use a single number for the acceleration? So the fact that the problem is only dealing with the kinematics variables and that they're implying the acceleration is constant, that would be one way you would know to use this approach. That's one way you can see maybe that we don't need to use, say, torque or conservation of energy or any of the more complicated ideas that maybe we'll get to later.
Perfect.
Just figuring out what the right approach is can be difficult sometimes. Another way to see that you don't use torque is they didn't mention any forces. So how could you use torque? We did a really good job here putting in all the signs. You picked out the right equation. The equation was missing theta. You rearranged it first before you plugged in your numbers. All right, and then you did 1930 divided by 81, and what did you get back from that?
I got 23.83 seconds.
Okay, so we can round that off to 23.8. That's good. The units here are complicated, but if you actually work through the algebra, the units come out in seconds, which is what we want them to be. We can assume that would happen anyway because we're using standard units. Now, mathematically, did our answer come out positive or negative?
Positive.
And that's what we would expect, because times are always positive. If this had come out negative, we would have known we made a mistake. We'd have to go back and figure out what it was. There's our answer, 23.8. It's good that you saw the hidden information. They didn't actually use the number 0, but they implied that the final velocity was 0 because we're coming to rest. You probably saw that trick when you're working with translational kinematics. Good. By the way, for part B, it's good that you saw that you couldn't just reuse your work from part A. You couldn't just reuse your work from part A because that was about 10 seconds, and part B might not be about 10 seconds. In fact, it wasn't about 10 seconds. You had to start over again.